time for Squeal Class. This is the third class. And last time you guys requested that we talk about decoding. So we'll get to that. But before we get to that, there was another question in the channel about dynamic where clauses, which I interpret to mean I want to be able to like specify for a given query what the filter is going to be. And so we did this example sort of last time where we said select user by name, and then we filter by a name. And we used another query that we had already written that selected all the queries, selected all the users, and then we applied a filter to that. So let's see something a little bit more general. We can say select user where, and we're going to put some kind of condition here, and it's going to give us back a statement db user, and we'll say select user where, and we have some where is going to be, it's going to be a query where we select star, so just like select user by name, from our subquery, which we already did, that selected all the users. Okay. And we'll add a little where clause that just lets us do that where there. So let's see what happens when we try to compile that. It says, oh, we found a wildcard that says condition ungrouped, this big old thing, which you know is the same as just the database, DB. And then at the end here, a table U whose type looks like the type for the user type. So if you look at the user type, it has username, user email, and favorite shawarma. And that's exactly what we have here, username, user email, and favorite shawarma. So that I know that this underscore here is going to be a condition, and it's ungrouped. It's got the empty lateral context and an empty common table expression context. And then we have our database that we're type checking against. And finally, oh, and we have one more here. It's the parameters. So that's what's corresponding to this empty parameters here. And then finally, we have a user table, which we can just say is row PG user. Let's see if that type checks. Okay, so that type checks, and we can do something like print SQL select user where username is like John. Oops, we need to turn on overloaded labels. And you see we get what we'd expect. Select star from select u.name as username, comma, e.email as username, blah, 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 as u. So here's our subquery. And then here's our filter where username is like John. Okay. And then an additional question was, okay, but I don't necessarily want just one condition. I might want multiple conditions, right? So what if I had multiple wheres?
Hey, Tom, I can't see your presentation.
Uh-oh.
Oh, wait, now it's suddenly back, actually. No. I don't know. That was such a terrible time to say that. It's actually just returned.
It's the same thing as last time. The frame per second for the updates is so slow. I get a new frame every 20 seconds. I don't know why.
It's probably just my internet is crappy. If everybody else would turn off any video you have, or I don't know. I'm not like downloading or doing anything, so I'm sorry, guys. I just have bad internet. We'll do the best we can, okay?
Yeah, it's a little snappier now.
Okay.
Are you on the VPN?
I'll go off the VPN. Yes, thank you for reminding me. And now I'm not on the VPN. Maybe it'll be a little snappier. Thanks for reminding me. Okay.
You might need to like come back into the meetup.
Should I turn it off and on? I'll do that. Okay. Can you guys see?
Yes.
So I'm working on select user where. And then what I previously had here was this. Or maybe not quite that. Okay, that. And we said now we can print our example of select user where I give it an actual list of, or an actual condition, select user where username is like John. Okay. But then the question that I had gotten previously was, what about if you had a list? You had a list of conditions. Can you give it a list of conditions? And sure, now we have multiple conditions, and we'll just say where where, a Haskell where clause, WH equals case WHS's of, if I have an empty list of conditions, then I just return true, which is this is lowercase t. It's not the Boolean, it's a SQL condition. Okay. And if I have multiple wheres, then I'll do a full del prime. Okay, let's see if that works. Oh, it doesn't like that. It doesn't know full del prime, so we'll import that.
Any particular reason for doing the case instead of just doing a full del prime with WHS and true?
Well, I kind of don't like that if it that it has that extra true, but there's no reason. I mean, it would be different SQL in that case, right? So let's see, in fact, the difference. We can.
Are we not confident that the SQL processing optimizing thing will not get rid of the true?
No. Oh, no, I'm not confident that that's true. That it won't do like the extra step of anding it with the true.
Maybe I use the double
erase it?
negative.
What?
I use the double negative by mistake. So I guess we don't know whether it will remove it nor whether it will keep it. We are uncertain.
Yeah. So yes, but let's at least just see the difference between those two, because it's totally valid to do it with the single fold instead of the case. So that would be, so okay, so here's what it looks like where username is like John. But if I did it just like this, then you see I get where true and username is like John, which logically means the same thing. So, and this is maybe a little cleaner on the Haskell side and a little dirtier on the Postgres side. Okay, so that was a question. I hope that means that Squeal supports dynamic wheres in the sense that people were asking about. And the next question we have is about decoding. So decoding means you run a query or a manipulation and you get back rows from that, and you want to see what it is you get back, and you need to decode it because Postgres is giving that back either in a text format or in a binary format, and Squeal only bothers with the binary format. And so we need to decode it from that binary format. And that means that at the level of individual Haskell types, which correspond to columns in the rows, columns in the return that the query is returning, we need to have a correspondence that says how do we decode that Haskell type from a Postgres. If we know it's Postgres type, how do we decode the binary into that Haskell type? And so that's what this from PG class is. And this from PG class, is it called inheriting? I don't know. It's got a super class, is PG. And what is PG is telling us is what the PG type associated to that Haskell type is. So first it needs an is PG instance, and then you can give it a from PG instance, which is just in this monad, right? So this is by virtue of what it is a monad. So you can can treat it monadically, but most of the time what you're going to do is derive this class for your Haskell types. So if you have a new type like user ID, which is a new type over int64, then you just put a little clause that says deriving new type is PG and from PG. And if you do that and you ask what is PG of user ID, it's going to say it's a PG int8. Okay, because it's clever enough to figure that out because you told it deriving new type, which means, hey, look at the underlying type and use its PG and its from PG, right? Another thing you can do is for your Haskell types, you can directly, if they're records, which this is actually very useful, is you can directly encode them as what are called composite types in Postgres. And for that, you need to derive some generic stuff. So stock will derive GHC generic. You need to turn on deriving generic for that. I don't know where that is in here. I guess because it's in the module, it doesn't need to explicitly import. And then you need to derive sop.generic and sop.hasDataTypeInfo. sop.generic gives us the product encoding or the sum of products encoding of this type. So this is a product of a double and a double. And then the hasDataTypeInfo gives me information about the field names, basically. Okay, so when we say deriving is PG, in fact, let's go ahead and do this example here. Okay, I need to turn on deriving strategies. Deriving via, derive any class.
Sam, I remember one time you called this Haskell 98, right? Because it's turning on 98 extensions.
That wasn't me.
I think it should be Xkitchen Sync. I want that extension. There's one other very interesting one that it's telling us to turn on called undecidable instances, which I think is maybe scary sounding, but isn't actually something to worry too much about. And the reason it's undecidable instances is because if we look at this instance where we're saying is PG via composite complex, then what it's trying to do is it's trying to calculate the PG type family of complex from something that's not smaller than complex, but is actually bigger, right? So inductively, it's not smaller. So GHC has no way of knowing that this terminates. But it's not a problem because what's happening here is that composite complex just looks at the has data type and the generic info to then build you a composite, a PG composite type. So we'll turn on X undecidable instances. And the worst thing that would happen is it wouldn't compile. It's not like it could cause a runtime error or anything. Let's try this one more time. And then we can ask, okay, great. So tell me, what is the kind, and this exclamation point means evaluate. What is the kind of PG complex? And it spits out something that it derived. It calculates that PG of complex is a PG composite whose first field is real, second field is imaginary, and it has float8s. Okay? So that's how you do encoding of individual fields. But obviously you need more than individual fields. You need, well, maybe before we talk about that, let's talk about this example, okay? So here's an example where instead of deriving the representation of complex, I'm hand rolling it. I guess this is called bespoke or something. I don't know, artisanal maybe instances. So here we're explicitly saying, okay, what is PG of complex? It's a PG composite, but instead of being the one that would be built generically, I want the fields to be re and im, okay? And now when I'm defining the from PG instance, I'm gonna use this row value function. And this says, okay, if I already know that PG of my type is a composite, the PG composite, and I know that row, give me a way of decoding that row into a Y, and I'll give you something in this monad. So this says, so I can say from PG is a row value, and then I'm going to be in this decode row, which we'll talk about in a little bit. And in that decode row, this decode row is a monad, so I can use do notation. And then we can see, what am I doing here? This is an example of row decoding. So my row has re and im. So from re, I can get out a value. And from im, I can get out another value. And then I just return complex with real equal to re and imaginary equal to im. And this is very useful if you have a Haskell type that doesn't have a derivable encoding into a Postgres type, because your Haskell type is maybe complex. It's not a simple record. It's, some ADT, and you want to store it as a record that's maybe overrepresented. Like for instance, if you had either, how would you encode either an either text int 64 as a Postgres type? Well, you might encode it as a row type, which has a nullable int 8 and a nullable text, and then you could say, okay, get the nullable in here, get the left value, get the right value. If both of them are nothing or both of them are just, throw an error. But if one of them is just and the other one is nothing, then return whichever the branch is, right? So this is very useful for doing something when it's not so easy to derive and you want to,
Yes, so just to make clear, if you derive from PG, it will automatically, for a sum type, it will automatically make a row with nullable fields. Is that correct?
No, it's not. It's not derivable.
Oh, it's not derivable. Okay, so you have to do it. You have to roll it yourself.
Well, right, because there's no first of all, there is no one-to-one correspondence between Haskell types and Postgres types, and some types in particular are not supported in Postgres.
Yeah.
But Postgres is a pretty strong type system. So you have composites and we have enum types. So if your sum type is nullery, that is if all the branches don't have arguments, right? It's just like day of the week, right? Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. If it's an enum type, then instead of then you can, right? So here's an example of an enum type: data direction, north, south, east, west. And for that one, we can go ahead and derive isPG via enumerated direction, right? So it's an enum type. So we say derive it as an enumerated. But also this leaves you open the option, right? So you're specifically saying in this case, I want it to be an enum type, but you could do a JSON. You could say, I want to store it as JSON. You could say, I want to store it as text. You could do, I want to store it as binary. There's all sorts of things you could do, right? So it leaves you open that option of how you want to store it in the database. Okay. So the next thing to talk about is this decode row type. And we already saw it being used in this row value function, which let us define from PG instances. So decode row is used in a number of places. The first place it's used is over here in the statement type. So you see that when you have a statement, let's look at the query version. When you have a query statement, then it wraps together your query together with a way of encoding its parameters and a way of decoding its rows. So our statement goes from X to Y, and we have a way of encoding our params from X and a way of decoding Y from our row. Okay. So let's go back to decode row. So decode row is some crazy thing. But the point is it's a monad, right? It's a reader T over an accept over a value, okay? And what is in the reader is a NP, so nullary product of a bunch of byte strings. This is basically a list of byte string, each one sort of tagged with its Postgres type, okay? And so we have a lot of instances for decode row. It's a monad. I said that already. So it's a monad, functor, applicative. It's also an alternative and a monad plus, just like most decoders would be. And then it also has isLabel instances, right? So the isLabel instances is what lets us do this stuff, right? So it says, okay, it has an isLabel instance because it has re in its columns. And so we can call that using a label and then get a value out of it. So together with all its monad, all its like functorial instances and its isLabel instance, it's pretty powerful.
Could you make it a monad fail as well?
Yeah, I probably should, right? Because it's a monad error. So you can throw error, but fail doesn't do probably what we would expect.
I'll go make an issue.
Okay, thanks. What else did I want to say about this? Oh, okay, there's one last thing, which is not only can you use a label to make a decode row, but you can also use a label to build a maybe T decode row. And so this is very useful. I don't know if I have an example of it, but if you have done like a left outer join and you have a whole bunch of columns that you know are now nullable because they're inside of an outer join, but you know that they're either going to be all not null or all not null, right? So you can run that in maybe T. Do I have an example? Run maybe T. So here's an example. So I have first is a null PG int and second is a null PG char1. And I want to give back, not that I want to give back the maybe int 16 and the maybe char together. What I want to give back is maybe a pair. Okay, so I can use maybe T. I can say the first thing, the second thing, pair them together, and then run it in maybe T. Okay, this is a smart constructor, so if you want to just directly define what the decode row is, you could do that. This lets us run the decode row. So if I have a decode row and then I have a bunch of byte strings, then I can decode it. Generic row is saying, okay, if my Y is a record, right? If it's a record, and I have from field instances for each, so all zip means we go through both of the lists. So row and Ys are lists, and we go term by term, and we say that we have a from field for each term in here to each term in there. Okay, and then that'll give us a decode row. So that's generic row. And so what's an example? Here's a type 2 with first and second, and deriving all the instances we want. Then we can just say we can decode from this type, which matches very closely. This is the row type. So the first matches first. The not null PG int 2 matches the int 16. Second matches second. And not null PG text matches string. Then we can decode them by just calling generic row. And here you see we're running decode row. And here's our list of byte strings. Here's the first byte string, and here's the second byte string. Okay. And then we have this stuff you don't really need to know about. This is like plumbing classes. So we had from PG. From PG operated on a Haskell type and then a corresponding Postgres type. From value has your Haskell type, but then it has, instead of a Postgres type, it has a null type. So that means either a not null or a null PG type. And so that's just saying, okay, if I have a from PGY, then I'm going to have a from value not null PG Y and a from value null PG maybe Y. So this is where we set up the correspondence between maybe and nullable. Okay? And then from field just upgrades that so that now we also have field names. So it's for records. From array is used as plumbing code to deal with arrays and decoding. And then here I'm re-exporting state and accept. And that's just an annoyance of deriving sometimes, is that certain things have to be in scope for via deriving and generalized new type deriving to work. So that's all that's going on there. Any questions?
No questions for me. It's pretty clear, so appreciate it.
Okay. We have some extra time. I'm willing to end early if you guys want. Otherwise, we can talk maybe about the other side of it, encoding. It's up to you guys. Do you want to end early, or do you want to talk about encoding?
I'd be interested in the encoding while we're here.
Me too.
Okay. So encoding is for out-of-line parameters. So we have decoding, encoding, and we also have inlining, right? So we have two ways of getting our Haskell values into SQL, and one is with inlining and one is with out-of-line parameters. So encoding is for encoding your out-of-line parameters. Okay, so first thing to notice is that encoding depends on the database. And the reason this is because Let's see who's here. Bergie's not here. Okay, so the reason that is there's every type has what's called an OID. In fact, everything in the database has an OID, which is just a way of identifying where in the database you can find information about it. And when you create a user-defined type, then at the same time, it'll create an OID for that type. And we need to be able to know what that OID is to do encoding, particularly if that type is used as the element type for an array or inside of a composite, then we need to know its OID. And in order to be able to look up what that OID, it makes sense to have the database itself in scope, right? So if I want to find out what the encoding is of an array of users, then I need to look up the OID of the user type, which I can find because the user type is defined in my schema. Okay. So encode params is the inverse of, oh, it's funny that I did it in a different order. Okay, maybe before we get back to encode params, let's talk about 2PG, right? So 2PG is the sort of inverse of from PG. And it, just like encode params, it depends on the database. It depends on your schema, okay? And so once again, 2PG is in this reader T, give me a connection to the database, and then I'll give you back an encoding. And encoding is just a builder, and a builder is a strict byte string builder, okay? And the reason we need to be in I/O is because we might need to connect to the database to figure out what the OID is. So this encoding isn't pure. It actually uses the connection to the database potentially, although rarely. Okay. So the normal way we would, well, I don't really have any examples, but normally you would just derive 2PG_DB in the exact same way that we derived. We probably have some examples here. So here's shawarma. Do you guys see it on my screen?
Yes.
Shawarma is a enum type. It's lamb, beef, and chicken, or chicken. And we can derive is PG and then 2PG_DB from PG and inline via enumerated shawarma. Okay, so then we can ask, okay, so tell me what is, we've done this before. What is the kind of PG shawarma? It's a PG enum of lamb, beef, and chicken. Okay, and the 2PG_DB, well, that's just how we are able to use that. And the inline also, well, we can see, let's print SQL inline lamb. Okay, so you see it just prints it as a string, which is exactly what an enum label looks like. So now let's go back to encode params. So encode params, it's not a monad in X, right? There's a monad here. There's a reader T over IO, but the X is in the wrong position for this to be a monad in X. Instead, what it is it's a contravariant functor. Okay? So do you guys have any familiarity with contravariants?
Yes.
Cool. Okay, so I won't belabor that too much. So you
I
can
don't know. Does anybody else?
Yeah. Yeah. I don't know if we need to spend time on it, but
Okay, so the API for encode params is one, you can use contramap, right? Contravariant gives you contramap. It's such a cool name. And then, okay, we have generic params, just like we had generic row, so that if you have a tuple of params, here's an example of a data type that's just obviously a product. So you can just say generic params, and it'll encode it as a tuple, right? Nil params is if you have no params, right? And you can do this for any type X. So that's kind of interesting, right? No matter what type X I give it, I can make a nil params. And that kind of makes sense because what I'm saying is no matter what X you give me, the parameters I'm actually passing is nothing, right? So it's not that the empty is becoming X, it's that the X is becoming empty.
Is there a place you use this phantom parameter?
This?
Yeah.
Yeah.
Or okay, you do use it.
Yeah, because all the, so.
Oh, I see. You use it in a recursion. Okay,
Right,
got it.
exactly. So we want all of these X's to be in the end. They are the parameter that you are using in your statement. Okay. So this one is important. This lets us put two encode params together. Well, not two encode params. So, okay. If I have a projection from X to X naught, and I have an encode params on my parameters ties to X, and I have a way of decoding X naught from the parameter tie, then I'll give you back a way of encoding the parameters that conses tie onto ties back into back from X, encoding them from X. And it's obvious how to do that. First, I'll encode the head by projecting onto here and then using 2param to encode it. And then I'll encode the rest of them using encode params, right? So for instance, we could say first, then second, and then nil params, right?
Yep.
And that's a way of encoding a tuple here, okay? Now I have this one. This little operator is similar to this one, but this one is a cons operator, and this one is sort of like ending the list, right? So if I didn't want this nil params here, right, then I could have just put star dot and said first star dot second. Okay, so give me two projections, and I'll give you an encode param with two things. And you can use this to end your list. So for instance, here's a triple, and I want it to correspond with this triple here, right? And so I'll say, okay, project X, and then project Y, and then finally project Z. So you do this over and over and over, and then the last one, you can tail it with that.
Is that just a notational convenience, or is there any difference?
Yeah.
Okay.
No, it's just a notational convenience.
Okay.
And you can see, if we look at the source, that it's star dot is first dot star, and then dot star with nil params.
Perfect.
Okay. Here's a param, which is very useful. It's for, I just want to encode a single parameter, which is very often what you're doing. Okay. And this says if I have a way of 2-paramming X, then give me an encode params for that. I can append two encode params together. So here's an example where, so I'm doing the same example over and over where I have just a double, right? So here I'm going to contramap first over a param, and then I'm going to contramap second over a param, and I'm going to append these two together. So that's another way of doing the exact same encoding. Okay, and so that's encodings. And I think we talked about inlinings last time. These are even the most simple way of dealing with Haskell types or Haskell values and using them in SQL. Just inline them.
Yeah, great. Looks like other people dropped off, so maybe we could call it
Okay.
good for now.
Yeah.
Yeah, thanks very much. It was really great. Really helpful.
Thanks,
Thanks,
Ethan.
guys. Bye.
Thanks.